Welcome to Coding Adventures. In this episode, we're gonna build or try to build this fractal tree that you can see here. And this one is a very encountered problem in many programming languages, starting from the very first time when I was introducing the Logo programming language. Today we're gonna try to attempt to implement it with JavaScript, but we're gonna take an element from the Logo programming language, the turtle graphics. So let's get started. All right, I'm back. And I open here a web page that shows a few examples of Logo. So what is Logo? Logo is a didactic programming language created many years ago with the intent of teaching kids how to code. It has a very simple syntax, like you see here in these examples. But over the years, this phenomenal programming language was an instrument in education. Nowadays, it's not that much used. But nevertheless, one of the features of this programming language, so-called turtle graphics, is still encountered in many other programming languages nowadays. Perhaps for learning to code or to even in the kind of a more professional way. So let me scroll here on the page and you'll see, yes, this is the example, the fractal tree that we're gonna build today. And it's similar to the one that I just displayed you before, the animated one. And the way we're gonna try to do it today is to take this Logo program and translate it in JavaScript. And as I mentioned, we're gonna first try to build a toolbox in order to achieve this program, a toolbox with turtle graphics commands. As environment, we're going to use the codeguppy environment, which is a p5.js based environment. Now, coincidentally, this environment has already turtle graphics built in, but we'll try to ignore all that and just build a small little turtle graphics engine from the start. So if you want to take this program outside of this environment, perhaps in a plain p5.js sketch or on another platform, so you can just port it easily. All right, so what is this turtle graphics that was present in Logo? Well, it's a way to draw on the canvas in a different ways from the perspective of, let's say, from the perspective of the drawing cursor. It's different than how we used to draw until now using Cartesian coordinates, like line from this coordinate to this coordinate. In Logo, you're just imagining yourself as being a very little turtle on a canvas that tries to either go forward or tries to go left or right and so on and so forth. So perhaps it's better to explain this concept on the paper and then see how we can implement basically this mini turtle graphics engine that will allow us ultimately to accomplish this fractal tree. So we have here our canvas. And as I mentioned, until now we used to draw shapes on the canvas like a line by specifying, for instance, for a line specifying the x1, y1 coordinate and x2, y2 coordinates, right? The coordinate, the starting and ending point of this line. With turtle is different. With turtle graphics is different. So just imagine you are a little turtle in the middle of the canvas. I'm representing this turtle with a small triangle, but if you are very talented, you can build a little turtle, perhaps with some legs, like that. And as you can see, this turtle is oriented, so perhaps that's the reason that I draw it with a small rectangle, small triangle. It's facing forward or towards top of the screen, and this is how the turtle starts, right? Of course, there is no turtle. It's just a virtual turtle. But imagine there is a small turtle over there. And then you issue commands to this turtle. If you say forward, and perhaps you specify a number in pixels, like forward 100 pixels, what will happen is this turtle will just draw a line of 100 pixels. And then imagine the turtle is again here. Of course, you don't see the turtle. What you are seeing is just the line. Now, if you are issuing a command such as right, let's say right, and you say 90 degrees, the turtle will just turn itself to the right 90 degrees, nothing will happen, but the next, if you issue again forward, and let's say again 100 pixels, what is happening, you'll see a second line drawn like this. Now, of course, not seeing any turtles, you should see just two connected lines. So this is all about the turtle. As you can see, the drawing is happening from the point of view of this little turtle. So it's kind of a point of view drawing. You just issue commands to this virtual turtle in this fashion: forward, right, back, left, and eventually you can also instruct the turtle raise the pen. It's like the turtle has a pen just in case you want to advance the turtle to a certain position and not draw anything until there, and then you say again put the pen down and go forward 100 pixels and so on and so forth. So all this is possible with the turtle graphics, and as I mentioned, Logo programming languages came kind of built in around this engine. This turtle graphics is now encountered in other programming languages such as Python. As I mentioned, even this environment that we are using here, codeguppy.com, has turtle graphics, but we're gonna just ignore all that and just build our own turtle engine, and then we use it to build, hopefully, to translate this Logo code and eventually achieve one of these fractal trees. All right, so let's get started. Let's keep our notes handy, but nevertheless, we need to focus on the code now. So let's create here perhaps a class turtle. I'm thinking to simulate this or to build this turtle engine is a small class named turtle that will have a constructor that we're gonna not use probably. And then let's see what kind of commands do we implement. And we said we need a command to go forward, go left, right, these kind of things, right? So we need forward, we need left command to make the turtle go left. Forward is a number of pixels, basically here, like n. And then go left n pixel, n degrees, and go right n degrees. That's another command. So yeah, I think these are pretty important commands, right? And then maybe we should have also a command here called home that we should just move the turtle back in the center of the screen. I think it will be interesting, although yeah, let's keep it simple. Let's not have it this one, right? So how can we proceed implementing this turtle class? Inside the constructor here, let's have a few properties, internal properties, and this will be basically the attributes of the turtle. So two attributes, obviously the position, like the X and Y, and another attribute should be the angle, because that turtle, in the moment we issue a rotate, or a right or a left, it should rotate a certain number of degrees. So on the paper we put here 90 degrees, but we can rotate it 30 degrees, 60 degrees, and so on and so forth. So let's have basically a this.x, and we can initialize already based on how Logo language operates. The turtles on that convention, the turtle is first initiating in the middle of the screen. So let's do the same here. So initiating in the middle of the screen, and then let's have also another property, angle is 0. What is interesting with Logo and with turtle graphics is that I'm going back here to the notes. The turtle first is facing towards the top, so this is the 0 degrees. Normally on a circle, if you remember a circle, 0 degrees is here somewhere, and then you just, here is 90 degrees basically, right? So with turtle is kind of the entire quadrant is a little bit rotating 90 degrees, but we can implement this kind of behavior and eventually compensate in our code for those 90 degrees. So when we are saying the turtle is at 0 degrees, we mean pointing up, not pointing to the right like on a normal circle. All right, so what other properties can we have? That's it. Let's try to implement these ones first. And actually, let me move this one down, because I think the easiest one to implement are left and right, and then we're gonna see how implement forward. So left and right, exactly like we put there on the paper, they don't do any drawing, but it just reorient the turtle. So therefore, all we have to say is this dot angle. When we go left, we are actually increasing the angle. We add n to that angle. And then this one, this dot angle, we subtract n. Because like on a circle, the angles go counterclockwise, right? So left should add this number to the angle. So if you say left 90 degrees, we should turn 90 degrees. All right, it's pretty simple until here. So let's see how we implement forward. This is a little bit more difficult perhaps, right? It's and angles and center and measuring circle just makes us remembering the polar coordinates, and actually we have to probably make use of polar coordinates. So let's take a blank piece of paper and plan a little bit how we implement forward. So we have our canvas here, and let's say the turtle arrived in a certain point here at certain coordinates x and y, or turtle x and turtle y. And let's say that the turtle also has an angle already, right? Let's say the angle is 30 degrees. So basically from the horizontal here, the turtle has already an angle. All right. The angle here is that angle. I'm just putting here an A, perhaps 30 degrees. And what we need to do is to figure out the x2, y2 coordinates. So since we know x and y is the coordinates where the turtle is, we know this angle. We know how many steps we want to go, because we say forward 100, right? So we say forward 100. So this one perhaps, this one is the distance that the turtle should travel. We need to figure out this x to y2, because once we figure out, we can say line from xy to x2 y2. So what the user will say forward 100. Of course, until here, the turtle accumulates some state. It knows already about an angle and so on. So we are just passing d. So this one is d. The x and y is already known. And what we need to do is to convert this one in x to y2, because what we need to do is to issue a line, which is a p5.js command, from xy to x2 y2. So this is what we need to do when we are saying forward. We need to draw a line, but to draw a line, we need to figure out x2, y2. All right, so pretty simple. We encountered this problem before. We need to do a transformation from polar coordinates to, to Cartesian coordinates. And polar coordinates are these coordinates when we know basically the, imagine this is on a circle, and we know the angle and the radius of a circle. Like I mentioned, imagine this one is on a circle. We know the radius, we know the angle, and we need to transform them in some sort of coordinates in this Cartesian plane. All right, this is pretty simple to do it, and we did this problem before. We can just imagine we have here some lines. So this line and this line. Eventually we can name them. This one is the vertical one, right? dy. And from here to here is the dx, to say like that, right? And we know that sine of angle of A is dy over d. From here, we figure out that dy is d times sine of A. That's a pretty important formula that we're gonna use. And then in the same way, we figure out that dx, because we use the cosinus function of angle, is the adjacent leg in this right triangle, dx over d, which means that dx is d times cosinus of A. So if we know dx and dy, we can figure out the x2 and y2. That's because let's say x2 equal, so this one here, it's x plus dx. So it's x, right? It's x, which is here, plus all this one, plus dx. So it's x plus d times cosinus of a, that's dx. And this is an important formula. We'll have to remember it. We'll have to put it in the code. And similarly, for y2 here, y2.
To do that, you'll need to be online.
Oops. And y2 is basically y. Now, our coordinates go like this, so x gets positive to the gets bigger to the right, and y gets bigger to towards the bottom. It's the inverse of a normal Cartesian systems where the coordinates are like that. So this one is not our case, but therefore y2, as we go towards the bottom, we have to subtract. So it's y minus dy, right? We go towards the bottom, we subtract this one towards the top. So we subtract minus d sine of a. All right, so that's minus there is necessary because our system of coordinates is flipped. All right, so these are the two formulas that now we have to put in the code when we implement the forward function. Should be pretty straightforward. Let me take a quick glimpse at the formulas. All right, I think I got them. So let's go here in the function, in the method. We are inside the class, so this is a method. And say, let's say let x2 is basically the turtle.x, right? We don't have x, but we have not turtle x, sorry, this dot x. We have this dot x, and then we are adding d times cosinus of angle, this dot angle, and y2 this dot y minus d times sinus or sine of this dot angle. Let me review really quickly the formulas. D sine, right? This should be right. And now all we have to do is basically make a line from this dot x and this dot y to x2 and y2. Sounds about right. Let's try to test this class. So let's name this one Fractal Tree, and we're gonna save it. And I'm gonna also put the program in the chat in case you want to load it. It's not yet ready, but I'm gonna make sure to save it from time to time, so eventually you should see the program running. All right, so let's see how we use this class, and let's use it in a small program here. So let's instantiate the class. Let turtle t equal new turtle. Just use a simple variable. And now let's say t dot forward 100. We should go a line up. T dot right 90 should go to the right, and let's say t forward 100. We should go a line to the right. Let's see if this one is working correctly. Oops, d is not defined. Oh, forward d. This is the distance. All right, so we have up and to the right, right? Or no, we are here. Where's the middle of the screen? Let's draw. So we said forward, right? I'm a little bit concerned because I'm looking right now. D forward. Let's initially draw a small circle, basically, at 400 and 300, and a small circle from where the turtle starts. All right, so it starts from here. Yep, it's not totally right. And why is not? Both of these lines, they don't cumulate. They don't. Oh, yes, because after we issue a forward, the turtle should just move to the new coordinates. So this dot x equal the new x2, and this dot y equal the new y2. So that's for sure. Let's run it. All right, now we are a little bit better, but we said forward up. You know what? It's because we didn't adjust for the 90-degree displacement. We said that in case of the turtle graphic, 0 is up, not to the left. So probably all we have to do is, yeah, just add here 90 degrees. plus 90, and here plus 90. So when our angle says that it's 0, it's actually 90 degrees. So this looks correct. So let's run it. All right, now it's fine. We started from the middle of the screen. We said forward 100, rotate right 90 degrees, and forward 100. So looks kind of correct. And these basically are these kind of commands. Let's see what else we need. So we need a right, we have it. We need a forward, we have it. Here it says repeat 4 times. We can do a for loop, I guess, right? Turtle apparently had this repeat command inside, so we can do a for loop. Or you know what? We can build inside the turtle a repeat just to make it a little bit fancier. We don't have back and we have left. So we have left, we have right, we don't have back. Oops. So we need also a back with a certain distance. Back is basically like forward, but should go backwards on the same kind of path, right? So in a sense, it's forward. Let's see if we can get away with this one. Minus D, we're going back. Let's see. And we said that we also need a repeat. Let's see an n times. How can we implement repeat? Repeat is actually, we need to repeat what? We need to repeat a certain block, let's say a lambda expression. We're gonna pass it here like a function. Okay, so it's simple. We'll say for I equals 0, I less than n, I plus plus. So we repeat n times fn. Eventually you can pass I, just in case we are interested. So we have also a repeat command. All right, so program still runs. We don't, okay. Let's try to take now. So we have, looks pretty much we have all we need. So let's take this program from here, and okay, let's clean up here. Let's prepare our turtle, and let's see how we convert this one. I just put it. Let me just put it as a comment. I'm using this command. Let's see how we can convert it in a JavaScript, basically like a function, perhaps call it plant. Have this function called plant, and that takes a size and an angle as an argument. Let's see. Let's build it above. Or move this line down. Let's see. Function plant, size and angle. Take this once as argument. And then says here, if size is less than 1, we stop. Okay, let's do that. If size is less than 1, we stop. So basically we return from the function. Now we have to issue a right of a certain angle. We have say forward, size. Oops, we don't have right and forward, they are t dot, right? So let's create inside the turtle inside here. And then say here t dot right, t dot forward. All right, sounds good. Although perhaps no, let's have the turtle outside, like a global variable. We'll say right, forward. What else we need to do? We had now to repeat 4 times and some sort of code here. And notice here. The code inside the repeat structure is actually invoking plant again, which means this is a recursive function, and we just worked with recursive functions yesterday, so this should come easy. So let's issue a repeat. So we say t.repeat, and the prototype of this one should be n, how many times, and then what we want to repeat. So it says here repeat 4 times, and now in our case, we're gonna just create a lambda expression, and inside we're gonna just invoke plant again. Let's call plant. So it's a recursive function for sure. We're calling again the same function. We said size divided by 2 as first argument, and then difference random 160, 80. I don't quite get that one. Probably random 160 minus 80. Okay, let's try that one. Random 160 minus 80. And we're good shape. Here we should say it's back and then left. we have those commands defined. T dot back size, right? And then T dot left angle. All right, that will be quite impressive. So we translated this logo program that we extracted from this website. Let's put the source of the program here in the code. Perhaps we should keep it, right? Logo program from, all right. We translated this one into our own JavaScript implementation, but we translated line by line. We didn't even took the time to analyze what it's doing, but what we did before, we built a mini turtle engine, so hopefully that one will execute it correctly. So let's see what's happening here. I'm gonna save it. Always save when you run programs that have recursion, because you may risk freezing the computer. Let's run it. Oops, nothing. Oh, all right. Oh, because we are not invoking plant, right? So let's invoke plant with, and it's even here an invocation with 100 and 0, a starting argument. And then this one will be a recursive function. Here we'll get invoking again and again. Let's run it. It's not quite it's quite different than this tree here, right? So let's analyze the program and let's see where we have the error. Do we have it in the program or do we have it in the turtle engine? So it says here, if size less than 1 will return, right angle, forward size, right? Let's separate them here. So right angle, forward size, right angle, forward size. And then we are repeating this structure, which is an invocation to the function itself with size divided by 2. And here, this expression, difference random 160 and 80, I'm interpreting like random 160 minus 80. Probably is okay, right? And now we go back this size and left an angle. That's quite correct. And we tested the functions before, but you know what we didn't test it? We didn't test it the back function. We just assumed that it's going back on the same direction there. But who knows? Maybe it's not it's not going like we're supposed to do. So if we're forwarding a certain number of pixels in front, yeah, let's reinspect our engine, perhaps a little bit. So left, when we are adding the angle here, which is fine. We are adding n to this angle. When we go right, the angle should go less, right? So we are subtracting. Should be fine. Forward, we implement it in this way and we tested a little bit this one with that forward functions. Looked correct, at least to me. So what we didn't test it is the back with a certain distance if it's going. Okay, let's test that one and eventually test also the repeat. So for now, we're gonna not use the plant, but coming back to the beginning, saying again, T forward 100 should have a line up. All right, let's try T right 30 degrees and T forward 100. We should have a line a little bit to the right. All right, and now let's try T back 100. So how we implement it back with minus? Okay, so we say back 100. Okay, nothing happens actually because it's not a visual command. But let's issue now T left. Let's say we go 30 degrees to the left and now T forward 100. So we should have a line to the left. Oops, we don't have it. For whatever reason. So I expected when I said back to come here and go left and have a line like that. So let's see. We issue forward 100. So forward, okay, let me take a little bit of notebook and see what I'm planning to do here. Obviously, it's not working as expected here, so bear with me. So I want to issue a command forward 100, right 30, and then forward 100, back 100. We are here. Left 30. Oh, it's back, but it's still heading that way. So let's left eventually 60, and then forward 100. Anyway, we should have I should get a little bit of a Y structure here. In any case, we should not get from that line. So here, when I'm saying left 30, let me say left 60, and let's see. Oh, okay. So this one is fine. The line is fine here, but it's not coming back from where I intended. So the question is, why not? Because when I'm saying back, it's invoking again forward, which seems like a good logic, right? We calculate the new one as being this one plus d times cosinus of angle plus 90, because we have that calculation. And then we have a line. Now in case of back, probably we don't have to do a line necessarily. And then we store the new x2 and the new y2. And with forward is working great, but for whatever reason it's not working great with back. Let's test just back. So when we start here initially, let's say t back 100. Let's see if we get, yeah, we get a line back. And now if we have, actually let's start t forward 100, t back 50, and t rotate 90. We go halfway, and then t forward 100. If anybody on the chat spots any error with the code, let me know. Okay, t rotate is not a function. Yeah, t right. All right. Okay, so it's not coming back. That's the problem. It's not coming back. Although we are invoking here forward d is this dot x, and this dot x, when we are invoking back, should just set the new x here, right? Because that's what it's supposed to do. This dot x is basically this dot angle. So forward is working fine. I'm looking at forward because it has majority of the code. Oh, I'm just invoking forward. This dot forward. I know. I think I know what's happening. I mentioned that this environment has already a turtle graphics built in. So when I said forward, I didn't get an error because I was just invoking probably the built-in method. But what I intend to do is to invoke this one. So I was not invoking the right one. Let's see if this one is working fine. All right, it's going back 50 and to the right. Let's try the Y-shape structure to see if this one is working correctly. And then we're gonna move to see the plant in action. Yep, the Y structure is working fine. And now let's remove all this test code and let's uncover back the plant structure. And we'll run it. And we have a tree, a fractal tree. And if we should run it, yeah, we should get a different tree because of this random function here. Actually, let's have a function, a loop function, loop. Really quickly here, let's clear the screen and we'll just generate new trees all the time. Probably we'll have to reset the coordinates. No, it's working. I'm not sure how, but it's working. I thought that we have to instantiate a new turtle all the time because the turtle remains in the old position and doesn't start from the beginning. For whatever reason, it's working fine. All right. It's still a good practice to reinitialize it again. So anyway, for now, let me just place this one. Actually, I'll not place it in the loop, but each time I want to draw a new plant, perhaps I should just create that a home function for the turtle to come back in the middle of the screen because the tree should start from that position. So, but we don't have a home, right? But we can create a home and make these variables kind of just go back again to the initial position. Because when we do it, the tree should start, but I'm not sure why it's working. It's working. Anyway, that's a pretty impressive tree, and we didn't have to analyze what it's doing. But I just want to do one more thing. I think I want to draw on the paper how a fractal tree is supposed to be drawn by the code, and then eventually understand this logic here together, or just rebuild a new tree and have a totally brand new tree from scratch built using this kind of tactile graphics. Perhaps even a color tree like the one we had before. All right, shall we? All right, so let me switch back to the notebook here and let's understand how a tree should be drawn, or what this program is doing. So we are starting at certain point and we want to draw a certain line. This will be the trunk of the tree. And then at this point we want to draw a random number of branches. Here we draw 4 branches, I think, but we can start with 2 branches. So we can draw a branch to the right and a branch to the left. And that will be step 1, right? And now for each of the branches we want to repeat the structure again and draw. So supposing this one is the main trunk again, and we draw 1 branch like this and 1 branch like that. For this one the same. And now for all the 4 ones we want to repeat it again. So basically this one are initials one, the red ones, let's say, and then we draw the blue ones in the other stage. And then perhaps in the other stage, after we continue the function, we should draw other ones, like for each of these other branches 2 new ones at this kind of angles, right? So this is the kind of tree that a fractal tree should look like, and that logo program kind of implemented quite all right. But let's try to rebuild it again. Let's try to build a function. Let's see if we can build it a little bit different, and this time we'll also try to play with a little bit of the symmetry. Here on paper I drawn a very symmetric kind of tree, but the one that we had on the screen was not symmetric because of this randomness, right? So we had this, which is fine. I like actually not being symmetric because that looks more natural. But anyway, nevertheless, let's create a new plant tree. All right, so we have this one, which is good. We like it, but let's have plant 2. Let's see if we can do it differently. Do it step by step. All right, so when we're planning the function, in this implementation we had size and angle, right? That was how the logo program was, but I'm thinking we can start just with a size. We don't need an angle. We should start with basically angle as being 0, right? So that's what we should do. And then let's go forward for this size. We draw the main trunk, and now at this point, what we need to do, what I want to do actually, so we draw this one forward and we are this position. We need to draw the right branch, but somehow after we draw the right branch, we'll need to return back to this point to draw the left branch. So we can do it a forward and then with a back to come back here, and then we draw this one and so on. What we can also do, we can have a function on the turtle engine to remember a point. So instead of going back, which is kind of drawing extra lines there, we can let's plan some more functions for the engine. Perhaps one that gives us the position and heading. I think that's how logo language used to call this. So let's have like property, one called position and one called heading. We can implement them here. Position, and this one should return. We'll return the this.x and the this.y as a small array. And let's have one called heading. And this one should actually return the angle. This is where the turtle is heading. And return this.heading. All right. So now I'm thinking I can make use of these functions here and record where this what are the coordinates where this this turtle ended. So let's record them in some sort of x and y coordinates. Turtle dot position. We record the position here, and let's record in h variable, or yeah, h variable heading, where is source heading. And now let's repeat. We can use a for, or we can use the repeat that we just defined above. Let's use the repeat. We repeat. Let's repeat just 2 times, not 3 times, not 4 times like above, and repeat a code block, or a lambda function basically. And for this one, what we need to do here is we'll choose an angle. An angle should be a random. We can also go with a random one, right? Let's go with a random one. So let's choose an angle. So where we want to draw the branch, and the angle should be a random between, here was 160 minus 80. I'm thinking anyway, from the perspective of this sketch that we draw, it's we should go about random from 0 to 45, right? So we should go 0 to 45 as angle, from 10 to 45. 45 will be half there, right? And now with this one, let's issue a right for this angle. We go towards that branch, and we invoke again the function plant2. Yes, we invoke again the function just to draw it again. Eventually, with a different position, we minimize the position every time. Let's not half it. We can multiply by 0.5 or divide it by 2, but actually let's multiply it with a random number, so it will be looking more natural. Perhaps not half it like we said, but perhaps a random between 0.6, 0.7, something like that. Perhaps give a little bit of room there. And now after we repeat this one, that's why we save these variables. Let's make sure we come back to these ones. So t dot set position. Oh, okay, we don't have a set position. So let's set the reverse of this function. So these are the getter functions. Let's create a set position, which is a set function, and a set heading. All right, let's go back here. This is the position and heading, and let's have also a set position. And position is basically, we'll receive an x and y, right? And we'll say this dot x equal x and this dot y equal y. And let's have also set heading with a certain angle, and basically this one will set the internal angle, this dot angle equal h. So this is just setting the angle and position just like that. Alternatively, you can come back with back, but let's try with this one. So set position to the x and y that we have here, right? And also we need to set the set heading h. All right, let's look at the code. Do we miss anything? I don't know. Let's run it. We have to call the function actually. Instead of calling plant, let's not call it from the loop. Actually, let's have it outside of the loop for a second. So initially we had a plant like this. Let's have call plant2, and we are just passing 100. We don't pass the angle. That's how we design it. All right, maximum call size exceeded. Oh, it's normal. Because we have a recursive function, we need to tell it when to stop. And actually in the logo implementation said when size become less than 1. We can keep the same condition kind of here. So when the branches become so little less than 1 pixel, we need to stop here. So let's say if size is less than 1, we just stop the recursion, right? Because it will go in plant2 and sees that size is less than 1, it will stop. Let's run it again. All right. Doesn't quite look like a tree. So let's analyze it again. It's not looking like it. It starts to go in this direction, but somehow again doesn't come here. Oh, so maybe that's what we built here. Oh, okay, t dot heading. I'm invoking again something else rather than the right one. T.heading and T.position. Let's see if we got it right. All right, it's a different drawing, but still it's not a tree. Doesn't look like a tree at all. So we are reading the T.position. And then, okay, right here, T.right. I'm forgetting to invoke these methods on the actual object. Let's see if we get them right. Oops. At least this time is not artistic. It's not right at all. So we have, oh, and again, T.forward. Wow, lots of lots of small issues here. All right, it starts to look. It goes, but that's it, and it stops. It never comes back on the other side, so we repeat 2 times. Maybe it's right, maybe not. Let's run it again. So what will be the problem here? We go forward, we draw the main trunk here, and then we save the position and the heading. Hopefully we implemented this correctly. So position, we are reading this.x and this.ay, and heading, oh, this is this.angle, right? I think the internal property is angle, right? So heading returns this.angle. Let's run it again. Plant 2. All right. Starts to look like a tree, but it's all bended to the right. And it's normal because we always use here right. We need to use alternatively either right or left. So we get some branches to the right and some branches to the left. That's what we should do it. Or, you know what we can also do? Right and left are actually the same. They are just complementary. It's just a matter of sign if we are adding or subtracting. So what we can do, we can multiply with -1. So first time, let's say we go with positive angles, next time with minus angles, positive, negative. So that one should balance between left and right. So let's have here as a variable eventually. Let's call it next sign, right? What is the next sign of the operation of the? Should we move to the left or to the right? And let's say it's 1. And angle, when we create the angle, we should multiply it with the next sign, and then eventually next sign we multiply it by -1. Yeah, let's do that. Next sign, it's so angle will be either these numbers or the minus equivalent, and the next sign for the next time we multiply by -1. So we toggle between positive and negative numbers. All right, much better. All right, we have a much better tree. Now let's beautify it a little bit. Let's make the trunk a little bit thicker and the branches eventually colored and so on. So in Logo there were some commands to say that this turtle that I was mentioning had a pen, right? So pen has a certain thickness, a certain color. You could say pen up, pen down. So we can implement this kind of commands on our Logo class here, or on our turtle class. So let's implement perhaps pen size, and let's store it in a variable when we're just saying pen size, or the variable should be called this dot pen size, pen weight. Let's call it pen weight, or pen size. Let's call it pen size, then underscore, just to avoid overwriting this method. Is n, and let's have one pen color with a certain color, and say this dot pen color, it's C. And now when we're gonna draw, and actually forward is the only method here that is drawing, what we can do, we can issue a stroke, which is a p5.js command. Stroke is giving the color, so it's basically this dot pen color, and the stroke weight this dot underscore pen size, I think. And eventually we can also put a push and pop, so these attributes don't spill up in the program if we are putting other graphics here. All right, it's not a valid color representation. Oh, of course, pen color and pen size, but we should have them like also some defaults in the constructor. So pen size is 1, and this dot pen color is black. We're going with black and pen of 1. All right, and looks the same. So we can now go to our program here in plant 2. And eventually, before we issue forward for the trunk, initially we can create a, we can say t.pen size. And we can increase the size of the pen, eventually 10. Nope. The size of the pen is dependent because plant 2 is a recursive function, so it's dependent basically on the size. So size goes from, we initially call it with 100, right? We call plant. Okay, so the thickness of the branch is dependent on the length of the branch. Let's make it this way. So here, instead of saying pen size of 10, we can map the size that goes from 100. It's initially we invoke it with 100 down to 1, which is the last value, and then the thickness will be from 0 down to 1, or down to 1. All right, we have a much better tree. I think we can go even to subunitary units here, 0.5. Yep, they look a little bit translucid. Let's go a little bit down, 0.1. I don't know if it's necessary. Oops, maybe it's too much. 0.5. All right, and now let's also use the color and do the same, map the size. If it's the size bigger than, maybe just the leaves, draw them with green. So basically if the size is less than a few pixels, draw them with green. All right, so we should say t.penColor, and you can also use a map function, or you can use if statements outside, but we can use a map function here. Or actually no, because it's just either, we can draw them either black or either green. So let's say if size is less than 10, draw them green, otherwise draw them black. All right, let's see. It's much nicer tree. Let's play with this number 0.9. No, they're too thick. Let's play, bring it down. It's too airy, so maybe 0.5. It was a good number. All right, looks fine to me. You know what we can also play here? We are repeating twice, like we did on the paper. But what we can do in the original one was repeating 4 times. Actually, let's repeat a random number of times between 2 or 3. So maybe you have either 2 or 3 branches. So it's a random. Now need a fixed number, not a. So let's pick a random number from an array. So either 2 or 3. Let's see what's going on here. All right, I think here goes 3 branches. Looks more natural. Let's run it again. Yes, there are 3. 1, 2, 3. Much nicer one, right? 1, 2. All right. Let's now implement that loop function again. Function loop. And function loop is a special function here in the environment. It's invoked by the browser automatically 60 times per second and so on. So it's very good for achieving animations. So let's clear the screen and just have plant 2. Let's see. Oops. And now for whatever reason, the plant is leaving the screen. So, oh, I know why it worked before, because without coming back, because we had always back. Now we leave the turtle in between the trees. We need to bring back the turtle. So what we need, let's call back the set position here, perhaps before drawing the plant. Let's call t set position, And let's draw it in the middle of the screen for now. So the next tree, no matter how the turtle was, we should come back in the middle of the screen and draw the turtle. All right, so looking better. Perhaps give it a little bit down. So 400 and 400 or 500. Yeah, 500 is fine. And let's also pick one of those backgrounds that we have here on the platform, perhaps field, or yeah, field fine. Field or scene one. Let's say background field. And let's enjoy our fractal generated tree. Background field. And if we run it, isn't this beautiful? So let's try to put them side by side. So this one, let's draw the first one. But this one starts, let's inspect again the code. All right, let's also use a set position, because this one's, let's start it at 100 and 500. All right, but this is all green, because you know what, the turtle remained in that position. It's the turtle, we are using the same turtle. What we can do, use two turtles. That one solution, and actually we can do this one. So this is turtle 1, and let's say use turtle 2. And for this one, let's use, oh, but inside we are using already. What we can do, we can extend it and pass what turtle to use. That's one way of doing it. So turtle keeps all the, or implement that home command just to clean up the turtle. Or just let's use turtle 2, and inside plant we're gonna use turtle 2. That's what we are doing it. We can pass it as an argument. That's the right way of doing it. But for now, let's just use it, hard code it inside the plant. All right, and now that one is black. The colors, they don't spill from one to the other. Anyway, let's comment this one because it's slowing down, at least on my computer. Yeah. All right, so the program is saved there, and just to see what we achieved, we started from this logo program that draws a fractal tree. We translated into the JavaScript program. We implemented also a mini turtle graphics engine in order to support this drawing, and then we just repeated ourselves the implementation just to make sure that in a slightly different way, and also we added colors just for fun, just to repeat the things. So instead of using back here, we just store the coordinates, and we are coming back to those using set position and set heading instead of using back. So two slightly different implementations, but nevertheless both of them are really fun, really nice. The first one is coming from that logo website. You can feel free to inspect it if you like it. And with this, I want to say thank you for watching. Have a nice weekend. Happy coding, and see you next time.